Good morning, everyone. Welcome back to the class. I'm sure now DP you have understood slightly, and DP based road cut solution we have discussed last time. I'm just showing you the sample code which can be applicable. Here I have also used the array C to store the corresponding cut information whenever the cut is being updated. CJ is also updated. So each time RJ as well as the CJ are being generated. And of course, returned value is revenue max or return this. So I will say return here. Finally, I can return Rn, and that is what I am supposed to return at every stage. And in between, every CJ is also updated. REST coding is more or less the same the way I have already discussed. So it is effectively that instead of having a recursive call, this becomes a non-recursive call to the stored value. REST logic is all same, but we have just done. So this is RJ being calculated. So with this, I'll just wanted to share, but maybe you have implemented and good enough. So now we resume and talk of further discussions. So having known all these concepts now, I can effectively see that when DP applicable, I have clearly understood that I require that I have an optimal solution to be computed from optimal sub-solutions. So optimal solution to be computed, but it requires solutions of sub-problems or optimal sub-problems, and they are overlapping in nature. So then we are able to ultimately get the solutions done, and then those solutions are being modified or being updated through non-recursive implementation, and I am able to do all that work without difficulty. So having said that, now I can say, let's go in a formal manner how dynamic programming and steps will be done. So I say dynamic programming solutions or methodology effectively will consist of 4 steps. So I'll define formally, although we have already discussed those 4 steps while talking of the road cut problem. So I'll say dynamic cut methodology, I'll just describe it. So first step is always characterize the optimal solution or characterize the structure of an optimal solution. For example, in case of optimal road cut problem, we have discussed that ultimately some k we are able to find, and we said one road is divided at position k, other port is this, and my total profit is, let's say, pk plus rn minus k. Or in general, I could say if their size was j, so I will say rj this. So this was overall characteristics through which I could find out that this could be pk or rk, but effectively this is how I should move. Then I said, then the next step will be, I have to use recursion, or using recursion effectively, I have to define the characteristics or the structure of the optimal solution. Obviously, it is going to use sub-solutions. So define structure of optimal solution, overall optimal solution, not single. So overall optimal solution, obviously using sub-problems, which are again recursive in nature. So that was effectively when I said that I have to find for any, say I said Rn is nothing but, in this I said that Rn is nothing but maximum out of, I had value Pn, or then P1 plus Rn minus 1, P2 plus Rn minus 2, and so on. So in fact, to be precise, this now I could easily say that instead of writing this, I could write it finally Pn plus R0. So maximum out of this to be found, and this is programmable as a recursion. That was second step. Third step now comes, effectively we have to compute the values of the optimal solution, or I'll say compute the value of an optimized solution using bottom-up methodology. So from the recursive definition, I have been able to find how those non-recursively can be found in a bottom-up manner, and That fashion you have to use, and bottom-up basis, then you will be able to calculate one optimal solution. For example, I said that Rj to be calculated using some Pi plus Rj minus I, and this I could easily solve. And then maybe I have to repeat. And then finally, I will say construct the final optimal solution. So construct the final optimal solution effectively using the above computed values. Using the above computed information, or above computed and stored information. We computed also and stored also. Like we said that overall we were able to finally find Rn or each Rj, and even also stored I cut values and cut position also, that is a part of final result. So I could generate this Rn or full R array. Effectively, I was able to generate full R array and full C array. So that is overall steps. Having said that, now things are easy, and that has made the DP very easy to understand. So now we go to a standard problem which is discussed in this context. And one standard problem which is discussed all over the world in the BTech courses is called as MCM problem, or to be precisely called as matrix chain multiplication problem. Shortly called as, or abbreviation is used as, saying it as MC. As the word suggests, matrices are to be multiplied and there is a chain to be multiplied. So effectively, I'll say, for example, if I have matrix A1, A2, A3 to be multiplied, aim is obviously it has to be an optimal problem or optimization problem. I want to say minimize the multiplication steps. Why multiplication steps? Effectively, or when the multiplication steps come, just I'll put a flag here and say, if you have to multiply, let's say, matrix A with matrix B. If matrix has some complexity, some order of row A into column A, and matrix B is of order row B into column B. Let's assume this is the order. So, for example, if it is, let's say, 3 into 5, then this will be something of, let's say, 5 into 8 or anything. But these two will be same. Only then matrix multiplication allowed. So, if these are allowed, how many multiplication steps or what is the time complexity to multiply, that indirectly tells multiplication steps. How many multiplications will take place? If you remember, this multiplication effectively is going to lead into a new matrix of size 3 into 8. And if I have to implement this, the normal logic is that I use for I is equal to 1 to row A, that is, this is going to be the I element. Similarly, I will say for j equal to 1 to column B, so that final result will be generated via this. And ultimately, what I will require is through this process, I will be able to generate mat3 ij. So each ij will be generated. Now, correspondingly, I will go from 1 to row A, j goes 1 to column B, and mat3 ij I'm generating, which is the summation using mat1 and mat2. So what is our logic? If you remember, mat1's all elements of one row were to be multiplied. So this is mat1, and these were to be multiplied with all elements in each column of mat2. How many these elements are? These elements are nothing but equal to column A. Similarly, this is also nothing but equal to row B. So effectively, I used to have some initialization here, and then I have a loop for k equal to 1 to column A or 1 to row B, whatever you say, one and the same thing. So I just remove this so that you can read it or see the logic clearly. So 1 to column A, and then you do some calculations saying that some say variable val equal to 0, then you say val equal to val plus mat1 of something into mat2 of something. So mat1 of something, whatever parameters you require, into mat2 of something. And then ultimately, then you say, and then you ultimately you say mat3ij to become equal to val. So effectively, these many multiplications take place every time. Every time one multiplication takes to do values, elements to be multiplied. And if you say this complexity or this number of multiplications are effectively nesting, here also nesting, here also nesting. So I can say the number of multiplications are nothing but row A into, I will say this value I will use straight away, column A, or into, then I will say column B. This column A is equivalent to saying row B. This is equivalent to saying row B. So you can write anything, but they are equal. So effectively, this will become the order of the total multiplication for two matrices. And I want to minimize. Then why I say minimization is needed? For example, in this case, one could be that you multiply A1, A2 first, and then A3. So if you put it like this will be one choice. Other choice could be you multiply A1 later and A2, A3 to be multiplied first. So these can be two choices. Similarly, if I have A1 to, let's say, A10, you can see there will be lots of permutations of combinations. So again, I can say it is exponentially growing permutations and combinations. So it is definitely a problem which is worth considering. Whether it is having overlapping subproblems or not, we will understand. If they have overlapping subproblems and divide and conquer can work, then we will go towards the DP. But having said that, let's see why it is important and why I say that the answer for A1, A2 multiplication with A3 later will be different than if I go A1 later and A2, A3 multiplied first. So if I say that how these are different, let's assume A1 is of order of, let's say, 10 into 100. A2 is 100 into 5. A3 is, let's say, 5 into 50. So assume this order, A1, A2 multiplied first. So if I say A1, A2 multiplied together will mean number of steps are 10 into 100 into 5. That becomes 5,000. Then this order of this A1, A2 matrix will become actually 10 into 5 now. So this is a 10 into 5, A1, A2. This will be further multiplied with A3 now. So 10 into 5 being multiplied with a matrix of a 5 into 50. This total multiplication steps will become 10 into 5 into 50. This becomes 2,500. So I say total is effectively 5,000 plus 2,500. That is 7,500. On the other hand, if I multiply A2, A3 first, A2, A3 multiplication will mean 100 into 5 being multiplied with a matrix of 5 into 50. The total, this is order of A2. This is A3's order. So number of multiplication steps will be equal to 100 into 5 into 50. That means 5 into 5, 25,000. 25,000. Later, A1 to be multiplied with this group, A2, A3. A2, A3 order is, A2, A3 order will become 100 into 50. So this will be 100 into 50. A1 is of order of a 10 into 100. Of course, multiplication is compatible. So these two multiplications will mean the total multiplication steps will be 10 into 100. This 100 is the same. So number of steps 10 into 100 into 50, that becomes 5,000. So total, this is 5, 0, 1, 2, 3. So effectively this 1, 2, 3, 4, 4 zeros, 50,000. So total comes out to be 75,000. These two added together. One side I am having 2,500, other side 75,000. So obviously I can say that doing A1, A2 first, then A3 was better. But if I have A1 to AN, if I have A1 to A20, each have a different size, how will you solve? So lot of possibilities. For example, if I say it could mean, say A1 to A10 in one group, and then A11 to A20, they can be further sold. They can be further sold. Other choice could be that yes, A1 to A5 as one group, A6 to A12 as another group, A13 to A20 as another, and so on. So many permutations, obviously. So first thing is now we have to systematically plan the solution. For planning the solution, I have to plan how I will store the values. What will be the P array, profit array, or in this case, the order. So I have to store order of each matrix, order of A1 to be stored, order of A2 to be stored. For example, this order I say is some value 5 into, or I'll say 10 into 100. Obviously, this 100 is supposed to be guaranteedly available. Only then multiplication in this chain will be possible. So these values are same. So if I have n matrices, effectively each matrix has two values as order, 2 int. I'll say each matrix order requires a storage of 2 ints. But out of that, one value is our order of the storage. Order storage requires 2 integers. So effectively 2 into n integers to be total stored needed, but why 2n? These are common. So I say first thing what I will do is A1, A2, A3 to AN, their order I will store in array P. So P is again in DP problems, the P is used as an input. Earlier that was profit, now that is for used as this. So I will say P array will be an array of only n plus 1 values at index 0, 1, 2, 3, 4, and up to n. I say here I will store 10 into 100. So A1 order is P0 into P1. Then I say A2 order is nothing but P1 into P2. So P1 can be common. So I will store here 100 once, 5 stored, 50 stored, and so on. By this process, effectively only n plus 1 value stored. So each matrix AI order is simply, I can always claim nothing but Pi minus 1 into Pi. Indirectly meaning Pi is nothing but columns of matrix AI. Indirectly meaning that also it is rows of matrix AI plus 1. They are same. So only P0 being additional value for the A1's rows, and for everybody else only columns of the each matrix stored 1 to n I am able to store that. So that saves my time, that saves my storage, and I can easily operate on this. So now I say if I have matrix A1 to AN and I have their P as a 0 to n, storing the order of these matrices. I want to have the MCM to be minimum multiplications. Aim is to have a minimum multiplication, and for that you have to put parentheses, so that I say parenthesize your expression in a way that I know which multiplication to be done in what order. Parenthesize your A1 to A. For example, if I say A1, A2, A3 are to be multiplied like this, then A4, A5 like this, then these further to be multiplied again and like. So this is what I mean by parenthesis, so that it is clear which one is to be multiplied in what order. Now, obviously, if I say these many, there are plenty of choices. So I can see it's going to be having exponential growth or exponential time complexity if recursively solved. Obviously recursion, because all permutations and combinations to be generated. So even I say if I have A1, A2, A3, A4, so I can see a lot of choices, say A1, A2 as one, A3, A4 separate, and then these, or I could say A1, A2 first, then A3, then A4, then it could be A1 only, or then A2, A3, then it multiplied with this, then A4, or it could be A2, A3 first, then multiply with A4, and then only multiply with A1. So many of these possible, lots of these. For 4, you can see so many permutations. So obviously for n being bigger, it will be growing exponentially. But now we have to think how DP can be used, or how it is a DP problem, first of all. So for finding whether it is a DP problem or not, we have to probably see whether there is overlapping or not and how recursively solvable. So going further, I say first step will be always characterize your optimal solution, characterize the structure. So I'll say characterize the structure of optimal solution effectively means characterize the structure of a parenthesization. So how will you parenthesize? If you are able to characterize or plan that way, then you can have your step down. For that, now in all DP problems, we will always say, let's assume that if I have this to be multiplied, assume that you have God's special power. You have some supreme powers, you have some exceptional talent, and you are able to judge that, yes, I know where first bracket will be put. I am guaranteedly able to claim that, yes, somewhere I find K where I am guaranteedly clear that at this position, bracket is guaranteed. Let's assume this is guaranteedly correct. If I say I know this because I'm able to find that, so by God's special power, you know 1K first time. एक बार आपको पता है, so you can always use that. So I say, if I know that this bracket is correct, so I say, if you have to multiply your matrix, which was A1 to AK, I claim this solution is equivalent to saying that you multiply A1, sorry, this is A1 to AN. If I know my K, so I say I'm guaranteedly knowing that I have to solve A1 to AK as one group, and also I have to guaranteedly solve the other group, which means K plus 1 to AN. So whatever this sub-problem will be solved, this is sub-problem 1 and another sub-problem available to me. So I'm able to divide my solution through some special powers into two problems. This can be again recursive. So I assume the way I had earlier solved, this will be solvable again. This is again a recursive, obviously. So I say that, yes, now characteristics can be made. I'm trying to go towards recursive solution. But having said that, how much multiplication will happen? So if this returns minimum multiplications for overall A1 to AN, then this becomes multiplication of A1 to AK, multiplication of AK plus 1 to AN, plus I have to multiply these two submatrices. Two submatrices will come, and that solution will also be needed because A1 to AK multiplied will result into a new matrix whose order will be the rows of A1, that is a P0, and columns of AK, that is a PK. Similarly, AK plus 1 to AN multiplied finally will lead to a new matrix which order will be PK, rows of AK, and columns of AN. So these two matrices to be multiplied finally. AK has put one, so K at K I have divided. After division, of course, these are to be multiplied. So I'll say that correspondingly, I'll just use a new pen for a different color so that you understand better. So I say now, I'm going to have effectively this multiplication to be done here. That will mean these are to be multiplied. So my total multiplication is going to be this plus this multiplication plus these two multiplications, and these two multiplications will be P0 into PK into PN. These from where I get based on these two orders. So I can say now I am able to characterize and effectively completing my first step, that A1 to AK, AN, if I have to multiply, then I say it is equivalent to saying MCM to be done for A1 to AK plus MCM or minimum multiplication for AK plus 1 to AN plus P0, PK, Pn. So this value effectively I can easily calculate without much of a problem. So I can easily say this is directly from profit array and these are recursively solvable. So now I have my solution requiring two sub-problems. One optimal solution I have said required two sub-problems which are recursively solvable plus array-based value or array or input-based P0, PK, P. I'll say P0, PK, P. But of course, we don't have the God's supreme power given to us or special power given to us. Then how will I find K? K is unknown actually. We don't have those powers. And even if we have powers, we won't waste that power for solving such simple or such programming oriented problems. Maybe I will try to use that special power of intuition, or I can guess, or I can predict, or I can find the correct value for something. So maybe I will use that power for fulfilling my dreams or some other wishes which I have unfulfilled. But of course, I don't have at present that power. So how to find k? If I don't have power, then I have to try for everything. So I will say, I don't have a power, no problem. Try for every k. Try for every k. Who stops you? So I say, if you have some matrix multiplication, so a word I don't write again and again. If I say, if you have matrix multiplication to be done for 1 to n, I will say, I can try it to have k as equal to 1, k equal to 2, k equal to 3, and up to the last possible will mean that I will say, okay, let's have multiplication done in a way that I should find minimum out of many possibilities. One will become MCM of 1 to 1. So taken k as 1, that will mean the other part will have 2 to n plus P0, P1, and Pn. Then this is effectively meaning k equal to 1. So this is equal to k equal to 1 here, comma, say k equal to 2. Find out MCM with k as 2. So I'll say multiplication or recursively find solution for 1 to 2 plus MCM of a 3 to n plus P0, P2, and Pn. Similarly for k equal to 3 and so and so. What can be the last value of k? K can be that I have n minus 1. Of course, not n, because if k is n, then all values are in the same group, which we are already, so no parentheses happen. So possible values of k are, k can be 1 to n minus 1. Try for every k. And whichever is minimum out of this becomes my choice. Well, that becomes simple, but effectively by this process, my recursive definition can be made ready now. So my recursive definition of the solution can be planned of the optimal solution. The overall optimal solution, I can definitely plan. Effectively, this is my step 2. So I can say, if I want to find minimum steps for multiplying in general any matrices from I to j, because now I am making not 1 to n, because sometimes this recursive call will come where this is not 1. So my start index can be different. My end index can be different. So I need now not just 1 to n to be said. I should use different indexes. So I say, if I have to do MCM of I to j, it is going to be minimum out of something, minimum out of many values. What are the values? MCM of I to, I will say k is 1. So that is I plus 1. And then plus MCM of I to I will say 1 at a time. So k is equal to 1 will mean I will have correspondingly, as I said, 1 to 1. So k equal to 1, I have a cut at, or I have a parenthesis at k. So k I1, so I plus 1 to j, plus the corresponding cost of multiplying these two final matrices. What will be that cost? The rows of matrix AI, which is Pi minus 1. Then columns of this matrix last. So I is the matrix Pi. And then columns of the last matrix Pg. Just recall, here we had k as 1 and I as 1. So I had P0. Here also, if I is 1, this will be P0. K is 1, P1, and J is n, Pn. So I had earlier used P0, P1, n when my values were known to me that I was 0, J was n, J was n, I was 1, J was n, and this was k. So effectively the same thing I am able to rewrite in terms of I and j. So where I means the starting index and j means the ending index. And now I need these to be general because here they are going to be different. So this becomes one case. Then I will say MC of similarly I to I plus 1. And then accordingly this, or in general, I will say, why should I unnecessarily write so many things? Why should I unnecessarily write so many things? And I will say, let's write it in terms of this to be done. I will say, let it be minimum out of, for all k being 1 to j minus 1, because I have the last value as j, so I will say j to 1 minus 1, and I have to effectively find MCM of I to k plus MCM of k plus 1 to j plus pi minus 1 into pk into pj. So effectively, this becomes overall value for each k, and I have to find out minimum out of the two, out of all these values. And this effectively is programmable easily using recursion. So I leave here and ask you to think of doing this programming using recursion. This recursive definition is ready, and using this recursive definition, you can definitely find the way we did in DP. So you will initially take the value to be int max plus infinity. You can assume to be the minimum value, and then calculate this value for k equal to 1. So effectively for k equal to I2, or for k equal to, I'll say not 1, I'll say from k equal to I, you will start, and up to j minus 1 we will go. So I to j minus 1 you will go, and then accordingly this is one recursive call. So recursive call will come for I to k, another recursive call for k plus 1 to j, and then plus you have the p based value. And if it is less than min, if current min, or I'll say if min val is already greater than this value, so you will update. So that's a simple, very similar to you have been doing. It's effectively, it is nothing but finding minimum out of I to j minus 1 values. I'll stop here and say implement this, and then think of doing memoization. Of course, you can have a memoization done, store these, and then again the same logic with just small memoization will do that. So implement recursive, and if possible, the memoized one. So I'll say recursive MCM, yeah, recursive implementation for MCM, and you have to effectively find minimum multiplication steps, and I'll say try memoized version for it. Few lines only will be added, and then we will see that later we will go towards DP. But why I claim DP is applicable now, just we will explain. Let's say if I have n equal to 8. So I say A1 to 8 is to be multiplied. So it has many possibilities. For example, I say A1 to A5. So I'll say effectively, if I'm talking of multiplication to be done using MCM for 1 to 8, my MCM is going to be 1 to 8 is equivalent to saying MCM of 1, 1 plus MCM of 2, 8. And somewhere I'm going to have, let's say, MCM of 1, 4 and MCM of 4, 8. So take two cases, MCM of 1, 4 and MCM of, let's say, 1, 6 and MCM of 6, 8. So if my n is 8, I say one parenthesis I put is saying 1 to 4 to be multiplied and 5 to 8, not this. This is 1 plus. So I have this 5 to 8. This is 7. So I say 1 to 4 and then I have 5 to 8. Other side is I will multiply 1 to 6, so one parenthesis, and 7 to 8 as another parenthesis. Now, that effectively means ultimately 1 to x will further solve later. Recursively, it will also try 1 to 4 also. Obviously, 1 to 6 has all permutations. So I say, if I'm saying 1, 2, 3, 4 as 1, 5, 6, 7, 8, one side. Other side, I have 1, 2, 3, 4, 5, 6. Other side, I have 7. But 1, 2, 3, 4, 5, 6 will also have many possibilities, many P and C. It will definitely have 1, 2, 3, 4, 5, 6, and many more like that. It will also have 1, 2, 3, 4, 5, and 6. This will further have 1, 2, 3, 4, and many more like that. So if you see carefully, 1, 2, 3, 4 calculated here also, 1, 2, 3, 4 calculated here also, 1, 2, 3, 4 calculated here also. So all I can see lot of overlapping sub-problems. Similarly, if I say 5, 6, 7, 8, 5, 6, 7, 8, where it can be further parenthesized as 5, 6, 7, 8. It can also be parenthesized at 7, 8 with 6 like this. It can also be parenthesized as 5, 6, 7, and 8, and many more like that. But indirectly meaning 7, 8 here also, 7, 8 here also, and in another solution of MCM 1 to 8, 7, 8 here also. So when I'm saying MCM of 1 to 8 being tried, MCM 1, 2, 3, 4 will get calculated many a times. Similarly, MCM 7, 8 will get calculated many a times, and that is a kind of overlap. Hence, obviously, better solution possible via DP. And that is what we are going to try. So with this, I will stop, and next class we will characterize the bottom-up solution, and bottom-up will be ultimately used to come to the final solution. Having stopped here, I'll now say, okay, let me stop recording.